I've previously done a video on Lee Hart's clone of the Altair 8800 computer designed to fit into an Altoids tin. I have that example here, although it's upside down in the tin. This worked, and as I showed in my earlier video, it was fully functional, but it did have some problems. One of which was that it wouldn't completely fit into the tin. It was a little bit too tall. This was largely due to the height of the inductor on the switching power supply, which originally stood up higher than the 8080 microprocessor, but which I retrofitted on my own to a different layout that allowed it to lay a little flatter, but it still didn't help enough. It was still too tall. And also the connectors that joined the two circuit boards that are in there were too tall. They weren't the ones he originally designed in, and then after the prototype kits were produced, it turned out the originally intended connectors were not available. So he's done some redesign and some part substitutions and other things, and the new version is supposed to fit into the tin. So he's kindly sent me another kit so I can have one that proves out the revisions and also does fit into the tin. I've got this one in my unusual spearmint box. Most of them have the red, the peppermint flavored, and I have one that's got the cinnamon flavor. That'll be a nice alternate box to use with this. I don't think he sent me a tin with this. Most of his production kits do come with Altoids tins. This one did not, but I have enough of my own. This is not Lee Hart on the front. This is Josh Benson, who helped with the project, and he's featured here with his 8080 in the background and holding one of the prototypes of the Altaid 8800. There's also an IMSI 8080 that should be, it's in itself a clone of the Altair 8800, just by a different manufacturer. And the whole thing is written to look like an issue of Popular Radio Electronics, a fictional magazine, as if this was an originally announced production kit. So by Gil Bates and Chip Hacker, yeah. So I'm going to build this one here and do another follow-along. Alright, there are two boards in this kit, and their parts are packaged in separate bags. So I'm going to just do one at a time here. Here's the CPU board, as it's called. Front side, back side. And this is a Rev C board, which is the same board I had in my original Altaid 8800 kit. So no board change there. Here are the parts that were included for it. There are 12 micro tactile push buttons, 8 of them for address and data, and the other 4 for status and commands. There's an assortment of disc capacitors, ceramic capacitors. Most of them are pre-marked. A couple of them are not. There's a crystal. I believe this is the inductor for the switching power supply. It's a much smaller one than this big bruiser on the original kit. Although it doesn't look like the circuit board has been laid out differently to accommodate it, so presumably, even though that's a surface mount part, it'll line up closely enough with the pads on the circuit board to not require any jury-rigging. 3 different kinds of diodes, 5 discrete resistors, some resistor networks, a electrolytic capacitor, various pin headers, and sockets. The only socket that was included for this board is this guy right here for the microprocessor. The other ones are from the same series. These are all Milmax parts, ultra low profile sockets, but they're still screw machine sockets, so high quality, gold plated and all that good stuff. So I purchased these separately from DigiKey. If you're interested in the general types, here are the bags. This is the 16-pin dip. Manufacturer part number there starting with 115. The DigiKey part number is the big one starting with ED. And there's the manufacturer Milmax. That's for that one. And here's for the 14, I'm sorry, that's the 20 pin. Not using that here on this board. Here's the 14 pin dip socket. Same information. I have a couple of spare 40 pinners too. This is the part number for that. And I don't have a bagged designator, but this is a tube of the 8-pin sockets. Same series, so one can extrapolate those easily enough to get the part numbers. And I also bought some EEPROM sized sockets for the other circuit board, which I've got waiting. Now, something that's also included with the parts for this board are all of these LEDs in red, green, and amber. But there are these rectangular ones, which I'm not a big fan of. Since they bleed into each other, they sit right next to each other with no spacing. I do like them better than the ones provided with the original kit, which were similarly shaped, but they were not diffuse types, and therefore they're just like hard points of light. On my original build, I used some dialight high-efficiency LEDs in these colors, and I arranged them in a octal pattern of 3 bits, 3 bits, and 2, 3, 3, 2, 3, 3, 2, which after I got this working, I just thought was too confusing ultimately. Anyway, so I'm not going to use these that were provided with the kit. I'll just throw those in my parts bin for possible future use. What I have here are the HLMP-K150. That's a generic part number. It was originally, I believe, a DigiKey, not a DigiKey, a Dialight part number. I've been using these things for decades. It's not a new part. I don't know if Dialight's even still in business, or at least in this business. I think they may have turned to LED lighting and things like that for large spaces rather than small, low-cost electronic parts, but maybe they still make them. Anyway, they didn't show up on any supplier list. Lots of different manufacturers make the HLMP-K150. That's the red part. So I have enough LEDs here to make all of the address and data LEDs just red, as they would have been on the original Altair. And then I have somewhere some amber LEDs left over from building the original kit, which I'll use in the same way I did here, just for the status LED set. If you're interested in the specific parts, these are all T1 size LEDs. This is just my parts bin. And in red, green, and yellow, in the same series, these are the DigiKey part numbers. And Broadcom is the manufacturer of the particular ones I got, even though other makers do make them. So the red one is the HLMP-K150 that I already mentioned. The green is HLMP-1503-Z0002. And then the yellow is the HLMP-1401. So now I've added the LEDs to the pile of parts. My 3 sets of 8 each red LED and 1 set of 4 amber LEDs, no green ones. This one undesignated cap, which I could read if I got my jeweler's loop out, but I'm just using my capacitance meter, verifying that it's 330 picofarads. And then this other one, which is coming in at 10 nanofarads, which divided by 1000 for the order of magnitude comes out to 0.01 microfarads, which is what the bill of material calls for. And I have that little surface mount inductor here clipped into the meter, and it's reading 117 microhenries. Should be 100, so that's reasonable within tolerance. I forgot to mention the ICs that come with it. These weren't the only parts. There's the 32K EEPROM with the operating system in it. And there's a 32K static RAM chip, an HM6285 12BLP, and there's an Intel 8080A microprocessor. So there's those. And then there's this whole tube of 14 and 16 pin ICs that are used on both boards. I'm not going to break those out at this point in time. I don't need this socket because one is provided in the form of 2 SIP sockets for the 2 rows of pins on the IC, and that's because all these other parts mount in between the 2 rows of the IC, and that's actually what was done on the original kit too. You can see by the pattern that it's not a regular IC socket that the IC is plugged into. I'm going to deviate from the suggested assembly steps first. It doesn't recommend for or against IC sockets. Normally you'd put the IC sockets on first because they're usually the lowest parts, and it's the lowest height parts, and it's easier to put them in and then build up from there. But there are some extenuating circumstances here. I remember from past experience using the IC sockets on this row of chips doesn't allow enough width to actually put the IC sockets in and the LEDs in between them, because the flat ones that are provided with the kit are slightly thinner than the round LEDs here, and it's easier to sand the sockets slightly than to sand all the LEDs. So here's the dilemma with the IC sockets and the LEDs. It actually just about fits in there, but then the LED wants to sit at a bit of an angle. It's just absolutely tight, and I think it's better if those sockets that are going to be used alongside these LEDs are sanded down just a little bit to give it just that little bit of extra space so they fit in there a little better. What I remember doing actually on the first kit was putting in the LEDs first and aligning them with a straight edge, and then once they were in there, then going ahead and putting in the IC sockets. So I may use that same approach here. I also vaguely remember from the first one that these tactile switches, their pins are just ever so slightly larger than the diameter of the holes that are provided for them. I recall it was difficult to get them to go in and sit flat on the board. There was always at least one pin that didn't want to go all the way in. So as I recall, what I ended up doing was putting a sanding disc on my Dremel tool and just kissing the sides of these pins ever so slightly with that, kind of laboriously for all the switches, just to make them slightly smaller and then they dropped in okay. So I'm going to be doing that as well. So a bit of preparation to do before actually starting to solder anything on this board. Alright, all the LEDs are tacked in. This is what you get initially. But it's just enough to hold them on the board. Now what I end up doing is one at a time I touch the iron. I only put one tiny blob of solder, well, not a blob. I just melt a little bit of solder into one hole. I heat that up again and rotate the LED until it's straight. And then only when everything looks perfect do I go ahead and really solder them all. This is really the tedious part, but unless you build a jig to hold everything in precise position ahead of time, this is pretty much the way you have to do it. Well, now they're more or less straightened and flat against the board, but I still need to do some more alignment and tweaking. Okay, I've got everything lined up visually this way, and straight up and down there, sight along the length. Obviously it's not absolutely perfect, but it's pretty darn close. Alright, all the LEDs are on. Now I have to go and fit the sockets that are going to go next to these LEDs, trimming them down ever so slightly on the sander or with a file so that they fit in there nice and square. They almost fit. It's really just the tiniest amount that has to come off to make them really drop in there. Alright, I've put these up against my belt sander just ever so gently and taken them down just enough so they just barely slip in there. That includes this one SIP socket. I need to make sure that's up straight when I solder it. It wants to lean outward a little bit, but it will go straight. I just need to make sure it's that way when I solder it, so that the 1802 will, or the 8080 will plug in correctly. Alright, all those critical IC sockets are soldered in now. I'm going to hold off on the strips for the 8080 processor until I get those other parts mounted in between them. Well, I was going to follow the recommended instructions, except that it's still written for the through-hole parts, and there's that one surface mount part, which is the inductor. I think I'm going to have to solder that from the side. So this electrolytic cap here, that's the very first thing that they recommend be soldered first. Well, it's going to get in the way of soldering that inductor, so I think I'll do that first. Okay, I put a dollop of solder on the surface mount soldering tabs of the inductor, and little blobs of solder filling the holes where the through-hole lead inductor was supposed to go. So now I can set the inductor down on there and heat up one of the side tabs, and it should sweat the inductor into place. Then I'll do the other one. Okay, I've got that inductor sweat soldered down to the pads underneath it, and I've done continuity checks between the tops of the inductor terminals far away from the solder and the places in the circuit where they need to go electrically, so I verify there are good connections there. All of the capacitors are soldered onto this board now. Now 3 diodes and the crystal are soldered to the board. The instructions now call for adding the resistor networks, starting with resistor network R1, but that's the one that provides the series current limiting resistances for the LED, all the LEDs in their scanning matrix. So that's what determines the brightness. And I recall that on my first one I ended up with a 270 ohm resistor network to get a desired brightness, and the kit comes with a 100 ohm. I think it may be a little too bright, so I'm holding off on that one until I get everything else assembled. Then I'll just stick the network in there and push it against the sides of the holes and see which brightness works better. So that guy's being held in reserve. Then the resistor networks, except for R1, are soldered to the board. The rest of the resistors are soldered on now. The instructions now suggest putting on the 30-pin headers along the top and bottom of the board, but those need to align precisely with the sockets on the other board, so I'm not going to put those on until I've done everything else on this board. Then I'll start looking at the alignment of the two boards and their connectors. Okay, to get these tactile switches to fit into the tiny holes on the circuit board, I'm going to be using a cutoff wheel. Where is it? There. It's actually not a cutoff wheel, it's just a grinding disc. And if I can get this in the picture correctly, I just kind of have it spinning and touch it to the sides of the legs, just to take them down ever so slightly, make them just a little bit smaller. One down, 11 more to go. Okay, got all those guys finessed into there. Not soldered yet. My little screwdriver to help push the switches down from the top. It fits better than my fingertips. Applies pressure more precisely. And that little abrasive disc there does quick work with them. You have to be really careful though, because it'll go right through them and cut the entire pin off if you're not careful. Okay, all the switches are soldered on. I think I'm going to go ahead and put the SIP sockets on either side for the 8080 processor now. To assure best alignment, I've pushed the SIP sockets onto the pins of the processor. You can actually see where I went a little bit too deep with my sanding and started getting into the edge of the, I guess it's brass pin socket, but only just barely. And so there are the SIP sockets. Nice and straight. I've removed the 8080 obviously. So I think that's all the soldering on this board except for the pin headers that connect the two boards together. By the way, here's the part number of a Bourne's 220 ohm SIP network. It contains 4 isolated resistors of 220 ohms each. That's probably what I'm going to end up putting in here in the R1 position. I had 270 ohm equivalent on the first one, but I don't have a 270 handy at this point, so I'll probably use the 220 ohm one. Close enough, I think. So here is a big difference between the original kit that I have and this revised one. Instead of using these cumbersome connectors here, which were such a trial to put in, it has all these little socket pins, or pin sockets. and those need to be installed in the memory I/O board. Now this is Rev C of this board, and if I look at the same board from the first one, it doesn't even mention that here. It may say the revision somewhere, but it's clearly a different board. Parts have been moved around a little bit, and it has these extra large holes to accommodate these small sockets. Here's how those little sockets push onto the pins of the header. Those sockets get a grip on the pins even when they're out about that far. So the contacting point is obviously pretty near the open end of the socket, which is good because I think if they went all the way down, they would not work out very well as far as the necessary spacing between the boards. Well, I checked with Lee Hart, and he actually had sent me a message which I forgot about, saying that his preferred method of doing this is to install the female sockets, the socket pins, or pin sockets, depending which way you want to look at it, on the short side of the header. And once those are on there, then drive the pins through the frame until they bottom out in the socket pins. So you have the maximum length going into them. Then solder the remaining side onto the circuit board, and then potentially pull the boards apart and remove the plastic frame altogether. Okay, here are the socket pins stuck on the short ends of the headers. Now I'm supposed to arrange them like this and tap or press down on all the pins until they won't go any further down into the socket pins. Okay, I now have the socket pins stuck into the memory I/O board, and the plastic frame is still there. The other side of the pin header is sticking up through the CPU board, and this is all just for alignment. So now I'm supposed to solder these pin sockets, or socket pins, into the memory I/O board, then pull the CPU board off and remove the frame, I think, so that the boards can come even closer together, and then solder them into place on the CPU board. Okay, here is the memory I/O board with the headers stuck into the soldered socket pins and the header frames pulled off. Now what I want to do is place the board back on here. That's the CPU board. It may take a bit of finessing to get it through all the holes. since they're not exactly all straight when I remove the frame. Okay, those are all in there. Obviously the boards are right up against each other now. I'd like to give it a little space, but not as much as the original frame had, maybe half that much. These are roughly 1/10 of an inch, so I think I'll go with about a 20th of an inch, I should say. It's snowing again. Well, I found a little piece of one-side copper-clad fiberglass circuit board material that if you'd remove the copper from it, it would probably be exactly 1/20th of an inch thick. It's the closest thing I found in my shop that would act as a shim. So I'm just going to go with that and place a few of them strategically around here and then do the soldering. Well, I didn't like that at all. By the time those fiberglass parts get in between the cut-off leads on the circuit board, they end up spacing it just as far apart as it would have been with the plastic frames in there. So I need to do something else that considers I want these boards as close together as they humanly can go, but still not impact each other. And I'm thinking I'm going to insulate them with a sheet of Mylar anyway. Maybe I'll just put 2 sheets of Mylar in and then solder them. Then I'm getting the longest pin insertion and still not forcing them to be apart further than they need to be. Okay, the pin headers are now soldered to the CPU board, but I have to cut off the excess. Okay, there's the memory I/O board with its socket pins soldered in, and the CPU board with its pin headers trimmed on the top side of the board. So I think it's time to start assembling the memory I/O board now. Okay, here are all the parts for the memory I/O board. Not quite as many as on the CPU board due to the relatively simpler circuit. It's really just a RAM chip, a ROM chip, and a couple of buffers, and parts to support the cassette interface, and a couple other things. We've already looked at the circuit board. And of course there are still sockets. I haven't brought the sockets out yet. Maybe I should do that now. There are the other sockets that I purchased separately. The 2 sockets here for RAM and EEPROM were included with the kit. All the IC sockets are soldered onto the memory I/O board now. All but 2 of the capacitors are soldered on now, and those are especially tall ones that I want to finesse because I think they'll end up being the tallest components on the board. So once the other parts are in, I'm going to see if I can mount those in some other way to make them less tall, maybe even on the back of the board. And 6 diodes are on there now. And the discrete resistors. And the 2 resistor networks, black and red. The 6-pin header, which is used for powering the computer and for serial communications. Because I'm trying to go for the extra low profile this time around, it doesn't mention in the instructions, but the instructions I think are the revision before. Some of the improvements were made to make the whole thing a bit more compact. I've determined that the pins only need to stick out this much past where those black lines are to fully engage the contacts on the SparkFun USB to serial cable. any additional pin protrusion on that is just a waste. So I'm going to push the frame up a little bit on there so that the pins don't stick out quite as much. Okay, there's the 6-pin header with the one unneeded pin removed and the pin heights adjusted to hopefully not be any taller than the ICs in their sockets, and still long enough to fully engage the contacts of the SparkFun cable. And if it turns out I got it wrong, then I can still tweak them a little bit by just snipping off a bit. It's not that difficult to deal with. And the 3 transistors are on there now. Apparently omitted from the instructions, I sure don't see where it mentions it, although it is in the bill of material, is the stereo 1/8" phone jack, which is used for the cassette interface. Although I'm not actually sure if the firmware supports the cassette interface. It didn't, I think, on the earlier one I had. Now on this one, the circuit board wasn't set up to take the alternate jack that I purchased, so I just rigged it up with some wires coming around from the other side of the board and hot melt glued it to the board upside down. Now I believe that Lee made some adjustments to the circuit board and did supply the same jack. Unfortunately, this jack's only available in surface mount, and it looks like what he did, so that it wouldn't be like a surface mount part, is just put some holes on the circuit board, and probably I'm supposed to bend these tabs down and treat them like pins. So I'm pretty sure that's what needs to be done. So I bent the pins down like that. And so there's that soldered on now. Goes in nice. The tabs are not long enough to actually stick through the board, more than just by maybe the thickness of a piece of paper sticking out. So it's a little trickier to solder them, but still it does work out. Okay, I've improvised a little bit to get those 2 larger capacitors down with a lower profile. I laid this one on its back, pushed this transistor just a little bit backwards, and got it down so it's no taller than the transistor. There's just no way to get this other capacitor in this spot and not have it be the tallest thing on the board. So instead I put it down here on the back. I found a place to nestle it in between some IC pins, and it should be within the dimension I expected to have between the 2 circuit boards, although it'll be touching the back of the CPU board through its sheet of Mylar that I'm going to have in there. So I think that'll be much better than having it up here. Okay, there's the completed memory I/O board. The only thing that remains to be done to it is installation of numerous small jumpers on the back side of the board that configure the memory and so on. And it was kind of hard to extract that from the instructions, and I think these are the same instructions, or the same revision of the instructions, that I got the first time around, so I'm probably going to just crack this guy open and look at what I did on the first time around. Unless the jumpers actually look different than they did, and then I'll have to do some head scratching with the schematic. Okay, I didn't install the ICs in the CPU board yet, so I'll do that now. So there's the CPU board with all ICs except the 8080 processor plugged in. And that's for testing purposes. There's a series of tests that are supposed to be done to this board before plugging in the processor. Although I did those laboriously the first time around, and I'm almost inclined to just jump in and hope for the best, but 8080s aren't just falling out of the sky these days, so I probably should be careful and do the tests. Alright, after my business trip, I'm back home again and squeezing in a little bit of testing. It's been a long day of driving, so I don't have much enthusiasm, but I did do some basic voltage checking per the instructions, making sure that the switching regulator is providing its voltages and that the support chip for the 8080, which is the 8224, is putting out its proper signals and voltages, and that the appropriate power supply voltages are available on all these other ICs, including the processor socket and these 4 ICs. I've also verified that the reset circuit works by monitoring pin 21 here and pushing and holding the reset button, making sure I get the correct reaction. Up next is a perfunctory test of the keyboard and LED driving circuit. So I temporarily jump this pin here, which is the output 4 pin on the circuit, and ground it through this jumper back to ground here, and at the same time connect the reset signal here through another jumper to the out 0 pin, which is pin 1 here. When I do that, then the reset button should control this LED. Well, it's not going to here because I don't have my resistor network soldered in yet, but if I push on it with my finger, I can get it to make a connection. And then, see if I can get this, when I hold down the reset button for a couple seconds, the LED goes out. When I release it, then the LED comes back on. I'm not really thrilled at the brilliance on that, so I'm going to try the, and this is, by the way, the 220 ohm resistor network that I bought separately. So I'm going to try it with the 100 ohm. I think that's 100 ohm. Seems like it might be a little brighter. So now I've moved the jumper over to the out 1 pin, which causes, through the intermittent resistor network connection, the next LED to light up. And pushing reset causes the LED to turn off. Moving the jumper again, I get that guy. Moving the jumper again, I have that one. Oops, resistor network shifted on me. There we go. Rearranging the jumpers, I get over to this red LED, which is the rightmost one in this group of 4. Reset should turn that guy off. Does. Moving the jumper gets me that LED. Over to there. And over to there. The flickering is due to the intermittency of the resistor network. It's just on the hairy edge of making connection there. But it is responding. I changed the binary combinations again, and now I've got that LED. And the fourth LED in that set. And I'm getting the binary patterns for the 3 output bits that control which bank of 4 LEDs. This is one bank, this is another bank, this is another bank, and there's 1, 2, 3, 4 additional banks of 4 LEDs each. So I'm just working my way through the possible binary patterns, and to do that I've got the 3 output pins all on a jumper cable here, and I've got just a lead of this loose capacitor jumpered to ground, and then I can connect various combinations of those 3 bits to the ground lead. When I did the first Altair 8800, I actually did this on a solderless breadboard, and it was a little neater, but I'm just being lazy at this point and doing it this way. So this is the last LED in the test. I've skipped taking video of most of the tests just for brevity. This is the last one. So all the LEDs are working, and all the various combinations of binary patterns that can control the LEDs are all working. This is a little tricky to do with my camera setup, but I'm using my logic probe to probe the digital input signals for this first bank of switches. So I have that as a high signal, and if I could somehow manage to get my hands positioned, and when I push that button it does toggle that bit. And if I go to the next bit down here, then it should be the next button. Oops, slipped off of it. Okay, that was the next button. Now the third button. And so that was testing the first 4 buttons here, and now by moving the binary pattern around, and I should probably illustrate, even though I covered this in more detail on my other video, there are these 4 bits here, output 4 through 6, that give me a 3-bit binary control over this decoder here. And I'm only working on some of it because the switches, these 4 switches, that's the ones I just tested, they're all commoned with this line here, which requires me to have a 100 pattern on here. So A would be a 1 and B and C would be a 0. D is already tied to 0. And now I want to test the next bank of switches, so I need to energize, or pull to ground rather, this line, which requires a 101. So I need A and C to be pulled high, so I need to move the jumpers around. And then I'll do the next set of switches, but I'm not going to show that on the camera probably. I don't know, maybe I can rig it up. Nope, I don't think so. Just going to have to take my word for it. Alright, I've gone through the 3 banks of switches, and this is the 3rd bank, but the 4th switch here is on a dedicated circuit for reset, and it's not part of the matrix, so I'm only able to test 3 bits within that that set. But those all worked fine, so all the switches are working correctly. The next thing to do is to verify that there is a good clock signal, and that's obtained on pin 6 of this chip. I'm at 2 volts per division. I'm getting about 4 volt signal, but it doesn't have to be a full 5 volt signal for the clock. So I've got a square wave there. My horizontal is set to 0.2 microseconds per division, and it's 1, 2.5 divisions. Do the math on that and it comes out to 2 megahertz, which is what I should be getting there. And it should be 4 volts, which is what I'm getting. And then pin 10 should be the same thing, but at a higher voltage. So there's that. I'm on 5 volts per division now, so that's 10, 11, 12, 13 volts, and same frequency. And I am supposed to get a 12 volt signal at the same frequency according to the instructions. And then finally, one more clock signal with a somewhat different waveform but the same voltage and frequency. So that completes all the initial checks of the CPU board without the CPU being in it. Alright, there's the completed CPU board. All I really did is added that resistor network in there. I did decide on the 220 ohm resistor as the better choice. I really don't like those LEDs glaring at me, and they don't need to be overly bright to have the desired effect for normal operation. Anyway, I would plug the MIO board on now, except that I haven't put any of the memory jumpers on yet. That's work for another day. Here's the rear of the old Altaid 8800's Rev B MIO, or memory input output board, with the jumpers as I had it there. But I'm now looking at a Rev C board, and most of the jumpers are the same, but there's been some changes. Certainly it's different in this area. This area looks about the same as does this. These here are kind of confusing. The old one, for example, had jumpers on 3 and 4 there, and here they're on 1 and 2. And here on 4 and 5 for W2, and here it's on 1 and 2, and the same thing. It's almost as if the patterns are reversed, but the silk screen stayed the same. I'm not sure at this point whether the difference is that originally there were no default jumpers on the circuit board, and you had to put these on in order to make the connections. Per the information I received, these are now supposed to be already jumpered as required for the parts supplied with the kit, but they almost look like they're flipped 180 degrees. So like W3, instead of being jumpered 1 to 2, it should be on 3 to 4, and here it's on 1 and 2 and 3 and 4, but it looks like it should be 2 and 3 and 4 and 5. This one is jumper 3 to 4, but I think it should be 2 and 3. I have to compare where the foils go to determine which way is correct. But either the silk screen's backwards or the jumpers are incorrectly placed here. They don't seem to match up with any valid arrangement of the board, and I compared that against this schematic. On the other hand, this is a Rev B schematic that came with the kit, with this version of the kit. So I have to see if the foils look the same. If they are, then I'm going to presume that these default jumpers are just incorrectly done, because by default there should be a jumper on W1 positions 2 and 3, but it's on 3 and 4 there. And likewise for the other ones, it's like it's all 180 degrees flipped. Okay, I'm assuming that the jumpers are correct for the moment. If they're not, then the program isn't going to run. The firmware shouldn't run because the EEPROM will be incorrectly connected on its address lines. So I've got my power supply temporarily connected to the power connector on the back. I'm going to turn the power on, and nothing happens. Try resetting it. Nothing happens. It's drawing about 260 milliamps, and it's not doing nada. So I'm going to presume at the moment that those jumpers are incorrect. Okay, with the default jumpers cut and new jumpers installed. Okay, let's see what happens this time. Nothing. Alright, I've got the new Altaid 8800 sitting next to my original one, and it is running. For some reason it did not seem to be running when I was just hooking it up to the power supply. There may have been an issue with the reset doing it that way, or failure to have one of the serial lines pulled high or low might have been causing an issue, you know, constant interrupt or something like that. But now it's plugged in through the SparkFun USB serial cable and connected to my computer using TerraTerm. And once again, I'm going to have problems with focus on my screen, but I press H and I get the help menu. I want to do a data dump of the first 16 bytes of memory. So I do D for dump, 0000, that's the first address, space, 000F. Hit enter, and it dumps the first 16 bytes and gives me a sort of an ASCII interpretation of what those characters would be. So it's running. I'm not going to repeat the whole operator interface thing that I did with the first time around. This is as close as I can get those boards together, and that's because I have that capacitor on the back. So I'm not sure if that's a great idea or not. They could go a little closer together if it wasn't for that guy. But if I put it up here, I know it's going to be sticking up too high for that reason. So let's just try putting the Altaid in its box. Well, it does fit, but it's something sticking up just enough. Yeah, the CPU is still sticking up just a hair. Okay, I've desoldered this C10 capacitor, 0.22 microfarad, and to make it shorter, I'm going to use my pliers to bust up the coating up closer to the body of the cap so I can put it into the board a little bit further from the top. Kind of like that. Okay, I've relocated that capacitor to the front of the board. I've made my Mylar insulator. Could be just a piece of paper or thin cardboard, but I have a lot of Mylar, so that's what I'm using. Okay, that way these boards are down this close together. And that blue cap is here, sticking up just above the ICs. On the other hand, so does the serial connector, which I can cut short if needed, but that's the height it's currently at. Okay, it's inside its Altoids tin, and the lid goes down and does snap shut. It's tight, there's no rattling. In that sense, it's just like the member chip card or ELF Mini from Lee Hart that I did a video on just a couple weeks ago. There is just not an iota of spare room in there. Everything to cut down on the height has been done. Really the only thing that could be done to help it slightly might be to get rid of the sockets, but you need the sockets under the CPU to fit all those components under it. And the same thing for the RAM and ROM chips. Those have components under them, so those need to be in sockets. And if you do that, then you might as well put all the other chips on sockets. It doesn't make it any taller in terms of the overall assembly. You can see here that the CPU sticks up just a hair above the top, but that's the only thing that's sticking up above the top. Everything else is flush. So the fact that the lid doesn't have to sit quite down on the top of this in order for it to close is the only thing that's a saving grace there. It's stretched open as far as it can be and still latch, and it's really just on the hairy edge. You can see that. If I flex the case, it pops open because it's under tension, but it does close to the point of staying latched. So in that sense, it does fit. I would call this a success. Yeah, I just slapped another one of my vintage 8080 labels on the front of the CPU just to make it look a little nicer. Here's my Altair 8800 computer. It's actually a clone of the original. It's not an old one, but it works and looks just like the old ones. I've done a separate video on this, so I'm not going to revisit everything now. It's just a front end to the video that I'm doing here on the Altaid 8800 clone. But I do want to point out the basic user interface here because it's part of my discussion that I'm going to be doing. There are a group of control switches. A lot of it's just running the program, single stepping through the program, examining the next memory location, depositing something into a memory location, resetting the processor, and then this is memory protect and a couple of unused auxiliary switches. So if ignoring those, the functionality here is essentially the same as the functionality on the Altaid 8800. The Altair has 16 bits of address numbered A0 through A15, and that's just 16 LEDs for displaying the current address. It also has 8 LEDs, D0 through D7, which are for displaying the contents of the memory pointed at by the current address. Then there's a couple of status LEDs over here, and some more detailed status LEDs up here. These status LEDs are not reflected on the Altaid, but all of these LEDs are. The Altair also has 16 toggle switches, which are used to set either the address or the 8-bit data in a specific address. So these lower 8 bits do double duty for entering address or data. The upper 8 bits are primarily for manipulating the upper 8 bits of the address, but they're also called sense switches, and these 8 can be read by a running program and used as operator input. That is also possible on the Altaid 8800 because all of the push buttons are readable by a running program. So the user interface is substantially the same between a real Altair 8800 and the Altaid 8800. Okay, just a quick run through of the operator interface of the Altaid 8800 from a better angle than I had attempted earlier. I'm not really going to do any programming here, but right now it's connected to a USB power source, namely one of the USB ports on the front of my desktop computer, and I've already demonstrated how I can communicate serially with the Altaid and with a terminal emulator, do various manipulations, use the machine language monitor, and so on. But just from the front panel, we have the address depicted here, and this is the lowest significant bit or least significant bit to the most significant bit, 16 bits in total, starting with bit 0 going up through bit 15, and they're broken into 2 groups of 8 just for visual reference. Right now, because of the programs that are being run in upper memory or the usage of memory, you've got a certain pattern here. Not all of the bits are turned on. The upper byte they are, but not all of them are. But right now that's insignificant. It's running the machine language monitor, or the internal firmware at least, and it's not trying to allow me to use the operator interface. And it's just doing a simple tick counter in binary here using the 8 data LEDs. Now the original Altair also had 16 address LEDs and 8 data LEDs, just like this one does. So in that sense they're just the same. The Altair had quite a few toggle switches for toggling in address and data, and some additional switches for control of the computer itself. It's stripped down a little bit on the Altaid. These 8 push buttons here are used for setting address and data 8 bits at a time, and these 4 are used for special purposes. Normally the leftmost one is the run button. That's what causes the Altaid to run the program that you've entered starting at the address it's currently set up to. The next button over is the mode key, and that allows you to select whether you want to manipulate the upper 8 bits of the address, the lower 8 bits of the address, or the data. Using those 8 push buttons here, you can work on this part, or this part, using those 8 buttons depending on which mode you're in. The third button over here is the next key, and that's when you're just looking at memory. You can push that and it'll automatically increment to the next memory address. Pushing it along with F7, which is this button way over here, or D7, I'm sorry, D7, pushing that along with the next button causes it to decrement the address and go backwards in looking through memory. And finally, the button on the right is the reset button that resets the whole computer. The LED operation is a little more squirrely, and I don't feel that I completely understand how that works all of the time anyway. So I'm going to sort of ignore that for the moment. But let's say that I want to go in and directly manipulate memory. So I'm going to go and push the mode button once. And now it flashes the upper 8 bits of the address. And I can now use these 8 push buttons to toggle those bits. See if I can hold this a little more firmly. There, I've just turned that bit off. As soon as I start doing that, the data LEDs, instead of doing their tick counter manipulation that they were doing, they just show me the data that's in this particular memory location. So now all of these LEDs tell me a particular memory location, and these LEDs tell me what's in that location. Now I'm still manipulating these bits up here, so I can continue to toggle those off. And as I do so, the data in the data LEDs changes. So I'm progressively turning those address bits off using the buttons. And sorry, my hand is sort of in the way. I can't really avoid it. Okay, so now I've turned all of these off, and I'm going to push this mode button again. It remains on, but now the lower or the lower 8 bits or the least significant 8 bits of the address are flashing, and I can start turning those off. And once again, the data LEDs show me whatever's in that address. Now I'm at address 0 here because all of the address LEDs are turned off. If I push the next button, it takes me up to address 1 and shows me what's in there. I can push next again, and I'm just cycling through memory here. If I can get coordinated enough to push the D7 button and the next, I'm stepping backwards through memory. But I inadvertently turned this one on just due to lack of coordination with the buttons. Now I can push the mode button again, and now these LEDs, the data LEDs, flash, and I can change what's in there, except I can't, and that's because I'm working in lower memory here, and lower memory on this computer is memory that's being used by the firmware. Even when I'm using the front panel, that's all being implemented via firmware, so I can't really change this. So I'm going to push this again, and now I'm going to set myself to 8,000, and I have to turn this bit off. So I push the mode button again. So now I'm at address 8,000 hex. I push the mode button again to get the data, and now it's allowing me to toggle those bits on and off because that's RAM memory that I'm working on now. I'm not trying to overwrite what's in the EEPROM. So I could go in here and put in this pattern for this particular byte 8000. I can push the next button and go to 8001, and I could turn this bit pattern on, push next again, go to the next one and turn that pattern, push next again, turn that pattern on, and now I can, if I can hold the D7 button down and push, I'm going backwards and looking at what I put in memory back to 8000. Or I can now go next forward. Oops, I inadvertently manipulated something there. But anyway, that's basically the way it works. And if I go back to 8000, supposedly I could run this, but there's not any real program in here, but I could still run it. The run LED comes on, and I've got some sort of activity on here. It's running my little program, but it's nonsensical. So I'm going to push the reset button for 2 seconds, and it takes me back to its power up sequence, where it counts down on the lowest 4 bits of the address and then resumes doing the tick counter here. So that's the basic demonstration of the direct front panel operator interface on the Altaid 8800. I got an update from Lee Hart. I asked several questions about some of the issues I encountered during assembly of the second Altaid 8800 kit, and made a couple of recommendations and thoughts. And this being a pre-production kit, these 2 tall capacitors here won't be an issue when this is turned into an actual kit for sale, because they don't have to be these particular models, and there are smaller capacitors which would be supplied that would just drop right in and don't require any fudging around. Also, I'd commented, I think, on the fact that when I tried to power both of my Altaids up using just 5-volt power clipped onto the power connectors without using the SparkFun serial cable to power it, I didn't get any activity. The processor just seemed to be doing nothing, although I did catch a slight flicker on the LED over the next button. And that told me that the processor was running, I was getting appropriate voltages, and it turns out that's just a mistake in the assembly instructions. The assembly manual's undergoing quite a few modifications, with comments from myself, comments from other people, thoughts that Lee had separately from comments of other people, and turns out that some of the parts on the memory I/O board here need to be assembled slightly differently. A diode replaced by a resistor, a capacitor shorted out or not installed and its pads shorted out. A couple of things like that need to be done, and then that allows it to be powered separately or powered through the serial cable. As it is with the assembly as described in the current version of the manual, which is still a Rev A 0.1.2, still not the final version. According to that assembly, the serial line gets installed, or the serial components get installed in such a way that they hold some of the handshake signals in a state that prevents the processor from running the firmware as it normally would. It's still running, it's just not running everything correctly. And that's oversimplification, I grant you, but I'm just trying to condense it. And therefore it only will function normally when the serial cable is plugged in. Even though the serial cable doesn't have to be necessarily plugged into a computer, the interface chip that's part of the cable is able to manipulate those serial lines in such a way that it allows the Altaid to run normally. So if I were to make those changes to this kit or my earlier one, then presumably I could power it independently of the USB cable or with the USB cable. I think I'm just going to leave it the way it is. I don't feel like messing with these anymore. But at least it's good to know that I could do that in the future if I want to run these independently. Even right now, I've proven that I could just plug the SparkFun USB cable into a USB wall wart, and this would run. I just can't run it off of a simple bench power supply as is.